Hello everyone, welcome to Concepts in Chemistry YouTube channel. So today in this video we are going to start a new series, that is multiple select question series, or you can say MSQ series. So usually we will see normally in GATE and IIT-JAM exam, and this type of questions normally GATE and IIT-JAM exam में पूछते हैं. So this video will be special for GATE and IIT-JAM exam, but हम लोग ये नहीं बोल सकते कि solving this type of questions or discussing this type of question answer will not helpful for other competitive exams like CSA, NET, BARC or any other competitive exam in chemical science. So this series of question answer discussions, means MSQ series, will be special for GATE and IIT-JAM, but it will also helpful for other competitive exam in chemical science. So let's start the first questions in MSQ series from chemical thermodynamics. So the first questions from chemical thermodynamics, 4 options are given. So normally हम लोगों को ऐसे ही क्वेश्चन देखने को मिलते हैं IIT-JAM और गेट एग्जाम में. MSQ सीरीज जो होता है 3-4 स्टेटमेंट वो लोग पूछते हैं, 3-4 स्टेटमेंट से ऑप्शन होता है कौन सा स्टेटमेंट करेक्ट है, 1 स्टेटमेंट, और if there are 4 statements like 4 or 3 statement A, B, C, then which is or which are will be correct, A, B, B only, A, B, C और B, C, इस टाइप का क्वेश्चन नॉर्मली पूछते हैं. सो द फर्स्ट क्वेश्चन फ्रॉम केमिकल थर्मोडायनेमिक्स इज दिस. 4 options are given. Chemical potential must decrease with increase in temperature at constant pressure. So this is statement 1. Statement 2, chemical potential must increase with increase in pressure at constant temperature. Statement 3, standard chemical potential is a function of temperature and pressure. Isothermal isobaric mixing of ideal gas is an example of isoenthalpic process. So these are the 4 statements. Among these 4 statements, which are or which is the correct options? MSQ सीरीज में 2-3 ऑप्शन भी सही होता है और कुछ केस में ओनली 1 ऑप्शन भी करेक्ट होता है. सो MSQ मीन्स हर बार हर केस में 2-3 ऑप्शन सही होगा ये नहीं है, कुछ केस में ऑप्शन एक ही ऑप्शन करेक्ट होता है. इसलिए मैक्सिमम केस में क्वेश्चन इस तरह का होता है, द करेक्ट ऑप्शंस इज और आर. इज मीन्स only 1 option possible, R means more than 1 option possible. So let's discuss every statement separately in details. Then we will see which statements are correct or which statements are wrong from these 4 statements given. So first 2 statements regarding chemical potentials, also statement C also chemical potentials, and D is the mixing of ideal gas. So let's discuss the first statements regarding. So we all know the chemical potential, definition of chemical potentials or partial molar quantity. So partial molar Gibbs free energy, that is GI bar. partial molar Gibbs free energy को हम लोग बोलते हैं chemical potentials. So partial molar Gibbs free energy is also known as chemical potential, and by definition we can write del G del Ni at constant temperature and pressure, Nj, J equal to not I, means we are differentiating this del Gibbs free energy means G with respect to a particular compositions, ith the component. We are differentiating G means Gibbs free energy with respect to a particular component, that is ith components, at constant temperature and pressures, and we also maintaining that the other components means Nj means except I, all other components remain constant. Only we are differentiating with respect to ith component by maintaining temperature, pressure and all other composition constant, and it is known as GI bar, means partial molar gives free energy, and it is also known as chemical potentials. So now we have to find the change. See the questions. Change in chemical potential with respect to temperature. So chemical potential must decrease with increase in temperature. So we have to find the effect of chemical potential by changing temperature. That's why we are differentiating here with respect to T. If we differentiate these equations with respect to T, then we will get by maintaining constant pressure. In the questions, at constant pressure condition was given, so we have to maintain at condition pressure constant condition. So now if we differentiate this chemical potential term with respect to T by maintaining P and Nj means all other components constant. Since we are differentiating this G gives free energy with respect to Ni, so that all other composition will remain constant. So from this expressions, if we apply Euler's theorem, so now this del Ni become outside del Ni, and this del T goes to the inside del G del T. We can write these expressions like this by Euler's theorem. So if we do this type of change, means del Ni become outside and del T goes inside, we have to change also the constant condition term. Means in this case inside the inside of the third bracket, constant is T, P and Nj equal to not I. Now since we change these two terms del T and del Ni, just they changes their places, we have to change this term also. Now del G del T, in this case this P Nj, this constant term goes inside, and this whole term constant T P Nj not equal to I goes to outside. So now it's become del Ni become outside, del T goes inside, del Ni, del G del T at constant P Nj whole bracket constant T P Nj not equal to I. This is thus we apply the Euler's theorem here. So now del G del T at constant P, we know del G del T at constant P equal to minus S. So del Ni minus S minus del S del Ni T P Nj not equal to I. See Gi bar, this is partial Gibbs molar Gibbs free energy, del G del Ni change in Gibbs free energy with respect to compositions, particular composition ith compositions, maintaining temperature and pressure and all other composition constant. This is known as partial Gibbs free energy. Now same, see here, change in entropy with respect to a ith compositions or component, maintaining temperature and pressure constant, and also the other composition constant. So we can say this term as Si bar, Gi bar, Si bar, and it is known as partial molar entropy of ith component. Normally we used to call partial molar Gibbs free energy as chemical potential. Gi bar is equal to mu I or chemical potential, but Si bar is not equal to mu I. We cannot say that partial molar entropy equal to Mi. This is partial molar Gibbs free energy, this is partial molar entropy. If there is other term Vi, H enthalpy I bar or Ai bar, all the term we have to call those term partial molar quantity, that is partial molar enthalpy, partial molar volume, but those term will not be equal to the mu I. Only Gi bar is only partial molar Gibbs free energy is known as chemical potentials, not the other terms. Si bar partial molar entropy is not known as chemical potential. Only Gibbs free energy bar means partial molar Gibbs free energy is known as chemical potentials. Now from these equations we can say that del mu I del T, change in chemical potential with respect to temperature at constant pressure. We establish the equations equal to Si bar. minus SI bar. And we all know that SI, entropy, is always a positive quantity. Entropy is always a positive quantity. So we can say from this whole expression, del mu I del T means del mu I del T, this whole term is mu I. So del mu I del T means change in chemical potential with respect to temperature at constant pressure equal to negative. Since SI bar is always a positive quantity and minus sign is there, so del mu I del T become negative always. So we can say from this whole expressions, chemical potential must decrease. See, chemical potential must decrease with increasing temperature. So this is the expression of change in chemical potential with respect to temperature at constant pressure. Since this the value of this term is negative, so we can say chemical potential will decrease if we increase temperature. Since negative sign is there, so chemical potential must decrease with increase in temperature at constant pressures. So chemical potential must decrease if we increase temperature. Chemical potential must decrease if we increase temperature at constant pressure. So this is the details explanations through establishment of some expressions of thermodynamic state. Now from this expression we can say that chemical potential should or must decrease with increase in temperature, because this is negative sign. If this is positive sign, then we can say with increasing temperature or with decreasing temperature, chemical potential will also increase or decrease. If we decrease temperature, chemical potential also decrease. If we increase temperature, chemical potential also increase if there is positive sign. Since there is negative sign, then we can say with increase in temperature, chemical potential will decrease, or will decrease in temperature, chemical potential also increase. So now see the first statement, chemical potential must decrease with increase in temperature at constant pressure. So the first statement is correct. We see here all the we see here by establishment of thermodynamic quantity, that is del mu I del T, change in chemical potential with respect to change in temperature at constant pressure, and this value become negative. So we can say chemical potential must decrease with increase in temperature at constant pressure. Now same thing, just see the second statement, chemical potential must increase with increase in pressure. Now we have to see the change in chemical potential with respect to pressure. In this case we just discuss change in chemical potential with respect to temperature. Now we have to see change in chemical potential with respect to pressure. So same thing, del mu I del Tp at constant temperature, we have to maintain the constant temperature and also Nj. Now it will become this, and if we use in this case, in this just in this expression we use Euler theorem. So this del Ni goes outside, del Ni, and this dP goes inside. So now del G del P also as similar as first expressions. In the third bracket, this term also changed their places. This Tnj goes inside this place, and this whole term goes to this place. Since we are changing this term dni and dp, also the constant conditions term also change their places. Now del G del P we can write from this expression del G del P at constant temperature equal to V. So now from these expressions, del V del Ni, temperature constant, pressure constant, Nj not equal to I. Now del V del Ni you can write Vi bar. Similarly as Gi bar, similarly as Si bar, we can write del V del Ni, change in volume with respect to a particular ith component, maintaining temperature and pressure constant, and also maintaining the other composition constant, that is Vi bar, means partial molar volume. We cannot say that this Vi bar is equal to chemical potential. Only from volume, entropy, enthalpy, and Gibbs free energy and Helmholtz free energy, only the Gi bar means Gibbs free energy bar, partial molar Gibbs free energy is equal to known as chemical potential. Partial molar Gibbs free energy is also known as chemical potential, but this term are only partial molar quantity term. Vi is partial molar volume, Si bar is partial molar entropy, Hi bar means partial molar enthalpy. These are only partial molar quantity term, and Gi bar means Gibbs free energy. Partial molar Gibbs free energy is also known as chemical potential. So mu I equal to Gi bar, but mu I not equal to Vi bar, Si bar or Hi bar. Only mu I chemical potential equal to Gi bar means partial molar Gibbs free energy. So from these calculations we found these expressions: change in chemical potential with respect to dP means with respect to pressure is positive. We know that volume is always a positive quantity. Likewise, entropy, volume is also a positive quantity. So now this term del mu I del P, change in chemical potentials with respect to pressure at constant temperature, become positive. So we can say from these expressions, chemical potential will increase with respect to pressure. So if we increase pressure, chemical potential increase, because this term is positive. If we decrease pressure, chemical potential will also decrease. So we can say for a substance, chemical potential increases with increase in pressure at constant temperature. Or we can say chemical potential will decrease, chemical potential decreases with decreasing pressure. Chemical potential increases with increasing pressure, chemical potential decreases with decreasing pressure at constant pressure. So in the second statement it is given like chemical potential must increase with increase in pressure at constant temperature. So we found here that chemical potential of a substance increases with increase in pressure at constant temperature. So statement 1 and 2 are correct. Now statement C, standard chemical potential is a function of temperature and pressure. So let's discuss this statement related some theory and calculations. So from the second calculations we found d mu I dpt equal to Vi bar, that is partial molar volume. So from these expressions, if we rearrange these equations, then d mu I we can write Vi bar into dP. So sorry, in this place should be P. So d mu I we can write Vi bar into dP at constant temperature and compositions. So for ideal gas, partial molar volume means Vi bar and volume are same. So partial molar volume, Vi bar and volume are same. So we can write Vi bar equal to V, and from the ideal gas equation PV equal to RT, for 1 mole we can write V equal to RT by P. Now we will put this RT by P in place of V. So d mu I equal to RT by P, we just put the RT by P in place of Vi bar dP. Now if we integrate with a proper limit the equations, then mu I 0 mu I d mu I equal to RT integration Pi 0 Pi, then mu I minus mu I 0 equal to RT ln Pi upon Pi 0. So if we put Pi 0 equal to 1 atm, that is standard pressure, we will write mu I equal to mu I 0 plus RT ln Pi. So this is the general expressions of chemical potential. This is chemical potentials of ith species. This is standard chemical potentials of ith species. So and this is the pressure of ith species. Pi 0 is the standard pressure, so Pi 0 is equal to 1 atm. So now in these expressions, mu I 0 is known as standard chemical potential and of the ith gas. So and this standard chemical potential we are putting Pi 0 equal to 1, then in these expressions Pi upon Pi 0, if we put Pi 0 equal to 1 atm, then we will get mu I equal to mu I 0 plus RT ln Pi. Now, standard chemical potential is defined as the chemical potential at 1 atm and a specified temperature. So, standard chemical potential mu I 0 we can define like that. It is the chemical potential of a substance at 1 atm pressure and a specified temperature. So we can say mu I 0 is independent of temperature, because we are defining standard chemical potential is as that it is a chemical potential at 1 atm pressure. So pressure is constant for standard chemical potential. 1 atm at 1 atm pressure, the chemical potential is known as standard chemical potential, and obviously as at a particular specified temperature. So standard chemical potential is defined as the chemical potential at 1 atm pressure and a particular specified temperature. So we can say that standard chemical potential mu I 0 is a function of temperature only, not temperature and pressure both, because chemical potential at 1 atm pressure is known as standard chemical potential and a particular specified temperature. So mu I 0 is a function of temperature. We can change the temperature, but if we maintain the pressure less than 1 atm or more than 1 atm, then we cannot say that this is a standard chemical potential. To obtain standard chemical potential, we have to maintain the 1 atm pressure. At 1 atm pressure, the chemical potential is known as standard chemical potential. So for standard chemical potential mu I 0, the pressure is 1 atm and temperature will be vary. It is either 100 Kelvin, 300 Kelvin. So we can vary temperature for standard chemical potential, but we have to maintain the pressure at 1 atm. So from these expressions, we can say that standard chemical potential is a function of temperature and temperature only. And from this whole expression, we can also say that chemical potential, not standard chemical potential, chemical potential is a function of temperature and pressure both. Temperature and pressure both. We will see later in our upcoming videos details regarding chemical potential, standard chemical potential. We can modify these whole equations, and in that equations mole fraction term will be there. Then we will see mu I, that is chemical potential dependency, in which functions chemical potential mu I normally depends, but mu I 0, that is standard chemical potential, only depends on temperature, not pressure. So from the third statement, standard chemical potential is a function of temperature and pressure only. So this is a wrong statement. Standard chemical potential is a function of temperature only, not pressure, because at 1 atm pressure, chemical potential is known as standard chemical potential. Now, isothermal isobaric mixing of ideal gas is an example of isoenthalpic process. Let's see some details regarding statement 4. So we all know for isothermal means temperature constant and isobaric means pressure constant. At constant temperature and at constant pressure, del G mix gives mixing of gives free energy equal to RT summation of Ni ln Xi. Xi is the mole fraction of ith component, Ni is the mole number of ith component at isothermal and isobaric conditions. Del G mix. Now from this equation dg equal to vdp minus s dt, we can write del G del Tp equal to minus s. Del G del T at constant pressure, this term will be 0 minus s. Now we can write del G by del T equal to del s. Since del G del T P is equal to s, we can write del change in Gibbs free energy means del G by del T at constant pressure is equal to change in entropy. Now similarly, del G mix del T at constant pressure, we can write del S mix minus del S mix. Now if we want to find expression of del S mix, now minus del T del G mix means change in Gibbs free energy. We found from these expressions del G mix, there is change in Gibbs free energy or mixing change for mixing of Gibbs free energy equal to RT Ni ln Xi summation of. If we put this value here, then we will get minus r, because this t become 1 after differentiation, minus r summations ni ln xi, ni constant, xi constant, so this time will remain same. Now from del z equal to del h minus t del s, from these expressions del h mix, if we write del h mix, then it will become del z mix plus t del s mix. So del z mix equal to rt summation ln ni ln xi plus t del s mix minus r summation of ni ln xi. So it's become 0. So del H mix, mixing of enthalpy is 0. We can say H is constant. Since H enthalpy is constant, so we can say that mixing of enthalpy or change in enthalpy is 0. So isothermal isobaric mixing of ideal gas is an example of isoenthalpic process. So del H mix 0 means H constant. dV 0 when it is possible, V is equal to constant. So dV 0 means V equal to constant, dG 0 means G is equal to constant. So any change, that is dV, dt or dA, dA is equal to 0 when it is possible, when the particular term G, T, V or H is equal to constant. So del H mix 0 means H constant. So we can say that isothermal isobaric mixing of ideal gas is an example of isoenthalpic process. H means enthalpy, H constant means isoenthalpic process. Like we say isothermal means dt 0 or T constant, isobaric means dP 0, P constant. Likewise del H mix 0 means H constant, so we can say this is an example of isoenthalpic process. So among these 4 statements, only the statement C is wrong, and A, B and D, the 3 statements are correct. We saw details by establishment of some expressions of chemical potential, standard chemical potential. We also learned something about partial molar Gibbs free energy. So by discussing, by solving this type of questions will also help you to revise some topic. Yeah, not only the questions, so not only we are solving the questions for exam purpose, also in this, by this series, a revisions of every topic, will be also done by this series. So this is the first MSQ series. I hope you all understood the questions and also their explanations to find the answer. So that's all for today. So in our upcoming video we will see lots of MSQ questions from different branches of chemistry, means organic, inorganic, physical. So thank you for watching, and okay, stay safe, stay healthy, bye.